Hello, so today we're going to learn our next method, which is steps to factor using difference of perfect squares. Sometimes this is referred to as dots. So the reason that we need this method is because sometimes we might look at a polynomial like number 1, a squared minus 4, and realize that there's no GCF there. So there's different methods we could use to create equivalent expressions. So before we get started with this method, I just want to remind you what the perfect squares are, because this will be important for this method. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 169, 196, 225, I'll stop at 15 squared, okay? So being able to recognize these and having these memorized is important, okay? So as I said, for number 1, we saw that we couldn't factor out a GCF. There was no GCF between a squared and 4. But what I do notice is that I have a difference, there's a subtraction sign in the middle, of 2 perfect squares. So the way that we do this is we're going to use the following rule to factor. When you have a perfect square minus another perfect square, you're going to create 2 parentheses. You're really just taking the square root of both of these numbers. So the square root of a is a, that comes first. The square root of b is just b. And in the middle, you're going to have the opposite signs. So a plus b, a minus b, okay? So let's look at number 1, a squared minus 4, okay? There's no GCF, but I do have the difference of 2 perfect squares. So I'm going to write 2 parentheses out. Okay, the square root of a squared is a. The square root of 4 is 2. And in the middle, we're doing 2 opposite signs. So just thinking about this, the reason why this works, and you don't need to write this down, you can just watch, is if I redistributed this, a times a is a squared. A times negative 2 is negative 2a. 2 times a is positive 2a. And 2 times negative 2 is negative 4. So the whole reason why we wanted those opposite signs is so our middle terms would cancel out when I combine my like terms, okay? So that's the reason for doing that. Let's do another example here. Okay. Number 2 is n squared minus 64. So notice, again, no GCF, so I'm going to use difference of 2 perfect squares because there's a subtraction symbol, and both of those terms in that binomial are perfect squares. So the square root of n squared is n. The square root of 64 is 8. Opposite signs go in the middle. Okay, so for number 3, we've got difference of 2 perfect squares. I could write 9 first because the square root of 81 is 9, plus x minus x. And again, you could always distribute like I showed in number 1 to make sure you're getting the correct answer. So 4 would be c plus 10, c minus 10. Number 5, there is no GCF, but notice how there's a plus sign here. This is not a difference of 2 perfect squares, so we can't actually factor this using this method. So we would say this is prime, or NF, which stands for not factorable. Okay. If I skip down to number 6, let's say, okay, same process. This is a difference. The square root of 1 is 1. The square root of 49y squared is 7y. So sometimes you have to be able to factor both the variable term and the coefficient that goes with it. So same thing like in number 7. I'm taking the square root of 9b squared, which is 3b. The square root of 100 is 10. So that's how I'd factor that one. So the last one would be 5x plus 7, 5x minus 7. Now, based on the commutative property, you could actually switch the order of these and you'd still be correct. So if you wanted to, you could write this as 5x minus 7 times 5x plus 7. And that's a 100% acceptable answer. Okay. And that's difference in 2 perfect squares.